Welcome to the Dallas Schools Environmental Education Center, a virtual field trip. I want to say a very special welcome to KB Polk, Dallas ISD. If you're watching and you have not signed up, please do so. Go to www.tiny.cc/6/8 registration and sign up, please. During this virtual field trip, students will compare metals, non-metals, and metalloids using physical properties such as luster, conductivity, malleability, calculate density to identify an unknown substance, and test the physical properties of minerals, including hardness, color, luster, and streak. Mr. Dominguez will do metals, non-metals, and metalloids. Mr. Monroe will tell you all about density. Ms. Schramm will discuss hardness, and Ms. Ramirez will do a program called streak. You cannot virtually ask us questions during this program, but you can go to www.tiny.cc/question-answer and send in your questions, and we'll do our best to answer them during the program. If not, I'll answer them and send them to your teacher. Now I am going to stop sharing my screen. And Mr. Dominguez is going to tell you all about metals, non-metals, and metalloids.
Hey guys, it's Mr. Dominguez here with the EEC. And in this portion of your virtual field trip, I will be talking to you guys about what makes a metal, what makes a non-metal, what makes a metalloid, using their physical properties. And you guys are going to help me spot those physical properties. But before we get started on that, I wanted to show you guys some household items that contain either a metal, a non-metal, or a metalloid. I have a soda can here, and the can is made out of aluminum. Aluminum is an element that is a metal. I also have a matchbox, and you may be wondering, well, what part of the matchbox is either a metal, non-metal, or metalloid? And we're actually pretty lucky here because we actually have 2 for 1. So the rough part, or the striking surface where you light your match, contains something called red phosphorus. It's a little more brown red. It's dull in color, pretty rough in texture. And if you open it up, you have your matches, of course, and the actual match head contains sulfur, which is also a non-metal. So we have phosphorus here and sulfur, so 2 for 1. That's pretty cool. And lastly, we have an iPad, and you may be wondering, well, are you talking about the metal that is, that makes the outer shell of an iPad in? Well, that's true. I'm not overly concerned about the outside. What makes an iPad an iPad is what's inside, right? So all the technology and all the chips and sensors and semiconductors, all that stuff is what makes an iPad an iPad. And all that technology would not be possible if it weren't for a very special element that is a metalloid. And I'm not going to tell you what that metalloid is. I want you guys to take a guess. So all your iPhones, all your Androids, all your consoles have this metalloid. All of our current technology would not be possible without this metalloid. So go ahead and take a guess. In the meantime, let's get started with our presentation. All right, guys, so let's get started with our presentation on metals, non-metals, and metalloids. So luckily for us, the periodic table is organized to help you identify metals, non-metals, and metalloids. So to the right of my periodic table, you have your non-metals. To the left, highlighted in yellow, are your metals. And what's in purple in that staircase pattern are your metalloids. And the metalloids are between the green nonmetals on the right-hand side and the metals on the left-hand side, and you'll understand why in a little bit. Now, what we're going to do is we are going to take a look at these pictures of metals. And what I want you guys to do, so teachers, take a moment to pause the video so your students can take a second or two to observe some of the physical properties of metals and see what they are being used for here. And hopefully, in the next slide, some of those observations will match up with the properties that make metals metals. So go ahead and pause the video and hopefully we get some matches. All right, guys. So these are the characteristics of metals. So they are shiny, they have high luster, they are good conductors of heat and electricity. So think of the wiring that's inside your home. All of that is probably copper or some other type of metal because metals are incredibly good conductors of electricity. They have high melting points. So think of what you use to cook with. All those pots and pans in your kitchen are probably made out of some metal, most likely either iron or copper. And that's because it takes a lot of heat to melt metal. So you would not want to cook with something that melts very easily. So they are malleable. That means that they can be hammered into different forms. So think of gold and how it's hammered or shaped into all kinds of jewelry. It is ductile. That means it can be drawn into wires. So let's go back to that electrical wiring. So luckily for us, we have metals that are very easily drawn into wire and just happen to be great conductors of electricity. They are also usually solid at room temperature. Now, that is for most metals. There is the exception of mercury, and because mercury had such a low melting point, is why we used it as a component of old thermometers because it was very reactive to heat. Now we're going to do the same thing again with nonmetals. So teachers, I recommend that you pause the video so you guys can observe some of the physical properties of nonmetals and also see what they are being used for here so we can talk about the characteristics that hopefully you guys talked about amongst yourselves in the next slide. All right, guys, so these are the characteristics of nonmetals. They are brittle, they are not malleable. So that means that if you were to hammer a nonmetal that was a solid, it would break. It would be broken into a bunch of little pieces. That's what brittle means. They are poor conductors of heat and electricity. They have low melting points, low boiling points. They have low density. So if you were to throw a non-metal into a bathtub full of water, that non-metal would most likely float because it has a very low density. And finally, it's dull. So non-metals are very dull. That means not shiny. All right, guys, one more time. And these are your metalloids. And here are some examples. So once again, take a second to look at their characteristics, pause the video, and we'll discuss what makes a metalloid a metalloid. All right, so some of the characteristics of metalloids are kind of taken from both metals and non-metals. So they're shiny, But as you saw in that last slide, we had some metalloids that were very brittle. That means they broke apart very easily. Uh, Metalloids are semiconductors. So that means that they're not as conductive as metals, but they're also not terribly bad at uh, being conductive with electricity or heat. Now, silicon is that very special metalloid that is inside my iPad, that is inside your iPhones, your Androids, your consoles, all this special technology that we probably could not live without. So the reason silicon is so important is because it allows us to turn the flow of electricity on and off, which is very important to technology. In fact, binary, or the language that computers use to communicate with one another, relies on us being able to switch electricity on and off. In doing so, we make binary possible, those zeros and ones that are the computer language. So, in other words, metalloids share properties of both metals and non-metals. All right, guys, I hope you guys can now distinguish between metals, non-metals, and metalloids. I'll see you guys next time for your next virtual field trip.
Thank you, Mr. Dominguez. And the question did come in, what are some other uses for metals? Shiny metals such as copper, silver, and gold are often used for decorative arts, jewelry, and coins. Strong metals such as iron and metal alloys such as stainless steel are used to build structures, ships, and vehicles, including cars, trains, and trucks. And now Mr. Monroe is going to tell you everything you ever wanted to know about density.
Good afternoon, students. My name is Mr. Monroe, and we're going to be looking into density. And that is a property that matter does have. Now, when we're referring to density, we're actually referring to the compactness of the material, of the matter. Actually, it doesn't have a lot to do with heaviness. I guess that would be a factor. But more importantly, it also deals with the space that matter is taking up. How close the atoms that make up that matter, or the molecules that make up that matter, how tightly they are packed or how loosely they are fitting into that matter. You know, all substances have density, including liquids, solids, and gases. Now, density, there's a formula that you can use to figure out the density of certain objects that are made up of certain matter. And that formula is this. Density equals mass divided by volume. Now again, density is the amount of matter per unit of volume. I'm going to use as a couple examples a cube and also a marble, because there's two different ways that the densities of these objects can be figured out. In the using of scientific equipment, we're actually going to be using a triple beam balance and also a graduated cylinder. So let's get started. I want you guys to pay attention now. We're going to start off by trying to figure out the density of this cube. Now, to save time, I have already did some measuring. First of all, the formula talks about determining the mass of the matter. So to do that, we're going to use the triple beam balance. And I'm going to put that on there. And we're going to see where it's at. I already kind of have an idea where it's going to fall. I'll just fine tune it. And I will tell you right now, it has a weight, a mass of 45.4 grams. Now, when we're talking about grams, usually they use the unit of measurement that we call grams. When we're talking about volume, we're talking about centimeters cubed, okay? Those are the two different measurements that we're going to be using today. So I'm going to write this down. 45, already kind of moved these in position there. 45.4 grams is what the mass is. Okay, you guys got that. Now, I also took a measurement using a centimeter ruler. And you take the length, the width, and the height measurements, okay? And I will tell you, since this is a cube, all of those are going to be the same. And I came out with, for the length, 2.5 centimeters, for the width, 2.5 centimeters, and for the height, 2.5 centimeters. Well, when you cube that, it comes to 15.625 centimeters. And I use my calculator, and I imagine your teachers will let you use a calculator when you're trying to figure out some of these, because you're going to have some decimals in there, okay? And when I came out, I divided 45.4 grams by 15.625 centimeters cubed, and guess what I came out with? I came out with a density of 2.9 grams cm cubed, okay? Now, if it's an irregular shaped object, of course, you're going to have to do something different, because you're not going to be able to measure the height, the width, or the length. And for this example, I took a marble, a very large marble, and I'm using a graduated cylinder, which appears like this. Now, to do this correctly, first of all, you have to get a set amount of water into your cylinder, your graduated cylinder, okay? In this case, I put it at 60 milliliters, okay? Now, I didn't put the marble in yet, because I'm saving that, because I'm going to have to take another measurement after I put the marble in. Now, remember this, there is something called a meniscus. And what that is, it's a little curve that's going to exist within that graduated cylinder. That water level, or that water line, is not going to be straight across. It's going to have a little dip in it. And so when you measure, you make sure that you're measuring at the point of the dip, not the edges, okay? Now, another key, you don't want this variable to be in. Whatever object that you're going to be putting in the cylinder, you don't want to just drop it in there. You want to be very gentle so you don't splash the water out. So I'm going to tilt this, and I'm going to gently, and I did get a drop. You don't want to do that, but we're going to go on because I don't want to run out of time. And what it's showing me now, it's showing me it's 70 milliliters right now. So the difference between 60 milliliters and 70 milliliters is how much? 10 milliliters. So there you have the volume. Now, I did have a chance to weigh this marble. And this marble, guess what it weighed? It weighed 20 grams. So I'm going to divide, in fact, I'll share this with you. 1 milliliter is equivalent to 1 centimeter cubed. So actually, I'm going to be using 10 centimeter cubed, and I'm going to divide it into the mass, which was 20 grams. So my density is going to be 2. Now, you know what that tells me? That tells me that that's pretty heavy density. In fact, if we were using the standard that most of the time is used, and that is water, water is a standard. A standard, when you're making a comparison of density, water is used because at the temperature of 4.0 Celsius, it's pretty stable. That's at 1.0. So what I'm going to do, I'm going to get the marble, and I've got a container here. I'm going to take this balance down. I've got a container here that has water, which is at 1.00, and I'm going to put the marble in. Did it float or did it sink? It sunk. So what that means is that water has a higher density or the marble has a higher density than the water because the atoms that are making up that marble are really, really compacted together real tight. So it has high density and water has a lower density. So guess what happened? The marble went down. I wonder what's going to happen with the cube. Let's see. The cube, it had a density of 2.9 grams / cm cubed, and it sunk also. Now, that's how you do those two, and there are other ways to measure density. One way is to constantly use water. If you're comparing other items that you want to look at their density, you can compare them. I'll tell you what, there's one I like to compare today, and that is a golf ball. I've been on the golf course. I tried to learn how to play golf many, many years ago. And I saw a lot of guys, they'd swing that golf club and they'd hit that ball and it'd go into the water trap or the small pond that's there on the golf course. And I often wondered, once that ball hit that pond, what was going to happen to it? Was it going to float or was it going to sink? And let's see what would happen. This is a golf ball. Wow, it sunk. So I can only imagine how many golf balls are on the bottom of those ponds at golf courses, okay? One more thing to think about, guys. This is real life. You know, last year we had a tremendous freeze here. I mean, it was a bad freeze. I lost a lot of the plants in my front yard that I'd had there for years. And I even looked at the ponds that we had out here. And there was ice on top of the ponds. And that ice was on top of the ponds. I don't think the whole pond was frozen, but I've got some ice that I want to put in this container, and I want to see what happens. Maybe you guys can see. I hope you can see. When I put that ice in there, what is that ice doing? Is it sinking? No, it's hovering near the top. So when these ponds and lakes freeze over, remember, only the top part, most of the time, is freezing. Because ice, we look at ice, the density of ice is 0.93. Water is 1.00. So what does that tell you about ice? Is it going to float or is it going to sink? Most of the time, the ice will float and be at the very top, okay? Now, I'm going to turn it back over to Dr. Gorman. So if any of you have any questions, I bet he can answer them for you. You guys have a good day.
Thank you, Mr. Monroe. And yes, the student did have a question. What is the most dense element? And it is an element called osmium, O-S-M-I-U-M. And what's it used for? It's used for the very tip end of very expensive fountain pens. Now, your teacher probably knows what a fountain pen is. Some of you guys may not, because most of all we use now is ballpoints. But some people still like the old fountain pen. So osmium is the most dense element known. All right, and now Ms. Schramm is going to tell you about hardness.
Hey, sixth graders. All right, so we are going to cover the hardness of minerals. So let me get this going. Okay, so we are testing the physical property of minerals, focusing on hardness. So before we get started, I want to go over the difference between rocks and minerals. So rocks have definite chemical composition. The color is usually the same. They usually have a shape, and there's no fossils, and they are made up of minerals. Minerals, on the other hand, are inorganic compounds. The colors are not the same. They usually don't have a definite shape, and they sometimes have fossils. Now, both are solid and both are naturally occurring. All right, but today we are focusing on the hardness of minerals. So the definition that we are going to use for hardness is the ability of a mineral to resist scratching. So our question today is, how can hardness be used to identify minerals? All right, so first we're going to start off with the MOHS scale of hardness. In 1812, a man named Friedrich Mohs invented a scale of hardness called the Mohs scale, which we still use today. He selected 10 standard minerals and arranged them in order of increasing hardness. So he has 1 through 10. Talc is the softest and diamond is the hardest. Each mineral can scratch only those below it on the scale. So let's check out those 10 minerals he selected. So 1 is talc, that is the softest. 2 is gypsum. 3 is calcite. Oops, sorry, I was supposed to be clicking. All right, here we go, caught up. 3 is calcite. 4 is fluorite. 5 is apatite. 6 is orthoclase, otherwise known as feldspar. 7 is quartz. 8 is topaz. 9 is corundum, also known as a ruby. And 10 is a diamond. Now you may be thinking those last 2 minerals, you may think of jewelry for a ruby and a diamond. You might think of them as being sparkly and beautiful, and you might think, why on earth do they look like that? Those are like the raw version of those minerals. So when you get them out of the ground, they don't look like they're ready to pop into an earring or a ring or a necklace, right? They're minerals that you need to polish and cut and shape to make those jewelries. So that is what the mineral looks like in its natural state. All right, there are also common items that we're familiar with in our daily lives that fit on the Mohs hardness scale to really understand the actual differences between these hardnesses. Okay, so each item is assigned a number. The first is a 2.5, and that is your fingernail. So if you were to take your fingernail on talc or gypsum, you would be able to scratch those minerals because it is higher on the scale. Now, everything else on the scale above a 2.5 is going to be harder and would in fact scratch your nail. All right, so the next item is a penny, and that is at a 3.5. So it is just harder than calcite, not quite as hard as fluorite. Then we have a knife, a kitchen knife, that is 5.5 on the scale. So it is harder than apatite, but not as hard as feldspar. So that's kind of almost in the middle of this whole scale. Then we have even harder, the steel nail at 6.5. Then we have a masonry drill bit. So the masonry drill bit is at an 8.5, and it's harder than regular screws or nails that you might use at home. I had to purchase one of these because our walls here at the EEC are made of brick and concrete, and I needed an extra strong drill bit to be able to get into the wall. So those are the hardest tool we'll talk about. Then we are going to check out this video. So there are actually Mohs hardness kits that you can get or borrow from the Science Resource Center here, and you can test the mineral hardness on your own. So we are going to watch this lady. This is another teacher, and she is going to kind of show how to use the Mohs hardness scale kit. Okay. So you'll notice she is only going to have minerals 1 through 9 because we're not giving out diamonds to children. All right, the first one, like I said, is talc. And remember, we said that they aren't always the same color. The picture of talc I showed you is much different than how this one looks. It's a completely different color. But here she goes using her fingernail, which remember was at a 2.5. So sure enough, she is able to scratch into the talc. Then we have selenite, which is also known as gypsum. And once again, her fingernail is a 2.5, so she is able to scratch the gypsum. Now we have a calcite, which is a 3 on the Mohs hardness scale, and her fingernail is no longer able to scratch. So she's gonna have to get a penny. Now the penny is, I believe, a 4.5. So she is going to scratch that. Okay, now she's got the fluorite. And yes, okay, I was correct, thank goodness. So the penny was able to scratch the fluorite because it is at a 4.5. Rats, I was wrong. The penny must be a 3.5 because she scratched it. See, that's why you need the MOHS hardness kit, because she's gonna test it out for you. All right. All right, next we have a steel blade, and she's able to easily scratch into the fluorite. Next comes our apatite. There's another example of a different color. The photo I showed you of apatite was more of a greenish blue, and this one is a bright green. And once again, the steel blade at 5.5 is able to scratch into the apatite. And that is Mr. Monroe's rooster. Hello, Smokey. All right, so at number 6, we have feldspar. So we've passed the halfway point, and the steel blade, let's see, is not able to scratch the feldspar because the steel blade is at 5.5 and the feldspar is at 6. So she is going to take the feldspar and test it on a piece of glass. Now, you'll notice if you do a MOHS kit in your classroom, you have to be really careful. She's taped the edges of the glass, and you have to be really careful to make sure that you place the glass onto the table, not holding it in your hand, because with that amount of pressure, you are putting on the mineral, or putting on the glass with the mineral could cause it to break. So she's got her glass laying flat, and now she's able to test the quartz as well. And sure enough, it scratches because quartz is at a 7. All right, next we have topaz. And so the topaz is able to scratch the quartz, but it's a little difficult because the shape of that topaz is kind of rounded edge. So I'm going to go a little further, but trust me on it that the topaz is harder. Eventually she gets it, but it takes a little minute. Okay. And there she goes. All right. All right, next we have that corundum. That corundum looks especially different than the one I showed you, and a lot different than what you might think of when you see a ruby. So if that sample was to end up in jewelry, it would need a lot of polishing and a lot of buffing and cleaning up. So corundum is the last one we'll show because, like I said, the diamonds are not included in the MOHS hardness scale kits because they are too expensive. But if she were able to take that diamond out, it would be able to scratch the corundum or the ruby. Okay. Whoop. All right, so I have a question for you, and this is a mystery mineral. So a mineral is able to scratch the blade of a knife, but is scratched by a nail. Using the MOHS hardness scale, what mineral could it be? So if you looked at the MOHS hardness scale using the common objects and the clues I just gave you, there would be one mineral on the hardness scale that would fit that description. So I'm going to let you figure that out yourself. And that is all I have for you. So thank you. I hope to see you at our next field trip.
Thank you, Ms. Schramm. And we did have a question. What is a layman's definition of hardness? And a layman, that's what most of us are. We're not experts on some things, so we're laymen. We want a very simple definition. And the definition is Hardness is a measure of how difficult or easy it is for a substance to be penetrated or scratched. For example, a steel nail can scratch your fingernail, so it is harder. And now, Ms. Ramirez is going to tell you about streak.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about mineral streaks. So before we begin, I actually have some mineral samples that I would like to show you guys. I do a lot of shopping at flea markets and places like that, so I actually like looking at some of the rocks and minerals that other people have found and collected. So here I have a cool looking mineral. This is rainbow quartz. So it's a colorful variety of the quartz that you guys saw in Ms. Schramm's video. I also have another example of quartz here as well. You can see all those beautiful iridescent colors for the rainbow quartz. Quartz can come in a variety of different colors. I also have another variety of quartz, the simple white one that you guys probably see. Very beautiful and sparkly on the inside of that one. And then I have another sparkly one. This is pyrite, also called fool's gold. It's not worth any money, but it sure is pretty. So that's pyrite. And then my last mineral is not pretty and sparkly like the other ones, but it is interesting. And that is gypsum. So you can see it's kind of like a flat sheet. And it's almost transparent. You can almost see me through it as well. So minerals come in all sorts of interesting shapes, colors, and sizes. I'm going to go ahead and share my screen with you, and we'll start our presentation on a mineral streaks. So let me get that presentation started. I also have two questions that I would like for y'all to keep in mind. Hopefully by the end of this presentation, you'll be able to answer them. The first is, what is a mineral streak? And the second is, why is a streak test used? And then on the slide, I just have some other interesting examples of minerals. Feel free to research some of those interesting ones on your own time. So I'm going to go ahead and move on to our next slide. So we're going to talk about what a streak is. The color of the powdered form of a mineral is its streak. And the way that we find that powdered form of a mineral is by simply taking that mineral and striking it across a streak plate. And it's just kind of like a plate made out of like a tile. So I'm actually going to stop my screen share, and we're going to do a demonstration of how to use that streak plate. So I'm going to stop that screen share and let me pull up my face full view so that you guys can see it. We're going to look at mineral number 1, which is this mineral right here. So it has a pretty interesting color. It's kind of like a dark gray. And I noticed that when I touch it, it leaves sort of like this fine powder on my hands, kind of like a sparkly powder. Reminds me of like eyeshadow or something, but it does leave a residue on my hands. And this happens to be graphite. So we're going to see what color the powdered form of graphite is. So I'm going to take my streak plate, I'm going to take my mineral, and I'm just going to drag it across the streak plate, and we're going to see what the streak color is. So here I go. And it almost feels like a smooth chalk, almost. And so you can see it has a rather dark streak, and it's almost like a grayish black color. So this is the streak, the powdered color form of the mineral graphite. Now, in this case, the streak color happens to be the same color as the mineral itself, but that's not always the case. So we're going to try another mineral, and hopefully you guys remember the name of this one. You saw a bigger version earlier. This one is pyrite, that beautiful fool's gold. So I'm going to see what its streak color is. So I'm going to take my mineral, take my streak plate. I'm just going to rub it really quick, and then you can see it left behind the streak. Now, pyrite typically has like a dark green, almost black color for its streak. So its streak is a little bit different than what its outward color looks like. My next mineral that we're going to test is this one. It's also pretty sparkly. It almost looks like graphite, but it's not. So this one happens to be hematite. And we're going to see what its streak is. So I'm going to take it and I'm going to run across through it. And just so you can see it better, it kind of has like a reddish brown streak. So in this case, the streak color is different than the outward color of this mineral. So that's hematite. My next one we're going to try is this pretty blue mineral. This one happens to be the blue variety of apatite. And what color streak do you think it might have? So I'm going to take my streak plate, I'm going to rub it across, and notice that I can't see anything. So most people think that when they see this one, they think it's going to have a blue streak. But again, we know that that's not always the case. the streak color and the mineral color can be different. So since I couldn't really see it on the white plate, I'm going to try it on my black streak plate, and we're going to see if we can see anything this time. So I'm making my streak, and of course you can see it leaves a white mark. So apatite has a streak color of white. And so the next thing that I want to do, we're just going to review a couple of things that we discussed. So let me share my computer screen one more time, and we'll pull up that presentation. So a couple of things I want to go over. So take a look at these 5 minerals here on the slide. Do you think that these are all the same mineral? Why or why not? So pay attention to the way the mineral looks and the way their streak looks. And hopefully you guys said that these are all different minerals because they all have different colored streaks. Now look at the set number 2. Do you think these are the same mineral? Why or why not? And I will tell you that all 3 of these, if you had a streak plate and you were to test them, they would all have the same reddish brown streak that you see here. So do you think these could be the same mineral, or do we still need to do more testing? So I'm going to go ahead and review what we have on the slide. Here for part 1, those are all 5 different minerals. They look the same, but when we do that streak test, they have different streak colors. So that lets us know that they are actually all different minerals. Now let's take a look on this bottom picture. All 3 of these are actually the same mineral. They are all a form of hematite. So even though they all look different, it's actually the same mineral. Hematite can come in a variety of different colors. The red one that you see is called earthy hematite. The pretty silver one that you see is submetallic hematite. And then the one that I showed you guys earlier, the shiny one, is metallic hematite. So those are all the same mineral, hematite. They actually all have the same streak color. So what this slide tells us is a streak is not always the same color as the mineral, but all samples of the same mineral will have the same color streak. So all samples of hematite will all have that same reddish brown streak. So unlike the surface of a mineral, the streak is not going to be affected by air or water. So the color is not going to change due to oxidation and things like that. So the streak, that powdered form of the mineral, the color, is going to be more reliable than just looking at the outward color of a mineral. Now, it is important to note that a streak test is just one of the many tests that you need to conduct in order to identify a mineral. Because keep in mind, some minerals might have the same color streak. So for example, that pretty blue apatite that I showed you guys earlier, there's other minerals that also have a white streak. So you have to narrow it down by doing even more tests. So you might have to look at color, cleavage, hardness, magnetism, and other properties to help you further identify minerals. And the last thing I have for you guys is a challenge. I would like for y'all to research a mineral and see if you can answer these 3 questions. So think about what elements make up that mineral, what is it used for, and what are some of its identifying characteristics. Now, everyone always likes to figure out their birthstone, and so I have a birthstone chart here. You can figure out what mineral correlates to your birthstone. I happen to be born in June, and my mineral, my birthstone is alexandrite, and it is a mineral variety of the mineral chrysoberyl. And I learned that that mineral is actually super rare, and it's also called the chameleon gem because it actually has the ability to change color and light. Now that is the natural form of alexandrite. However, nowadays in most jewelry stores, you can probably find much cheaper lab created versions of these gemstones too. And then here's some other examples of interesting minerals. These happen to be some deadly minerals. So you might want to explore and research why they are considered deadly minerals. And then my last little thing, if y'all need a place to go on vacation, or if you're interested on a quick little road trip, if you're interested in looking for rocks and minerals, I highly recommend the Crater of Diamonds State Park in Arkansas. It's only about 4 hours away from Dallas, and you can actually go there and look for your own rocks, minerals, and diamonds and things like that. So they have the collecting equipment and all the tools you need there. All you have to do is go look for them. And something interesting, back in 2015, a woman actually found a 3.69 carat diamond at that very same state park. And you can see some other examples of gems that people have found there, and you can actually keep them too. So something interesting. I'm going to go ahead and stop my share, and that's all I have for you guys on mineral streaks. We're going to give it back to Dr. Gorman to answer any questions.
Thank you, Mr. Maris. Very interesting and very beautiful examples of some minerals. We did have a question that came in, and it says, can we as students do some of these mineral tests, test these minerals? And if you're a Dallas ISD student, yes, you can. Your teacher can go to the Science Resource Center and check out these test kits, and you can do the test yourselves. Because I know it looked kind of unbelievable that a black rock would leave a blue streak or whatever, all the things, different things that she showed you. All right, now I'm going to share my screen. During after the program, you want to, and you want to ask questions, you can go to www.county.cc/question-answer, send in your questions. During this virtual field trip, students compared metals, non-metals, and metalloids using physical properties such as luster, conductivity, malleability, calculated density to identify an unknown substance, and tested the physical properties of minerals, including hardness, color, luster, and streak. Mr. Dominguez did metals, non-metals, and metalloids. Mr. Monroe discussed density. Ms. Ram talked about hardness, and Ms. Ramirez showed you how to identify streaks. Thank you very much, and we hope to see you in the future.